Okay, hello, welcome to video 4 of 4 of our hypothesis testing stats series. So today, or in this video, what we're going to do is talk about a t-test as a specific example of a way of testing a hypothesis. So let me activate that page. Okay, so we have already established that t-tests come in various forms. T-tests are used to compare something that has two conditions, so at a very high level, system A and system B. And you can either have paired t-tests or unpaired t-tests. So paired t-tests are when all the data points are contributed by the same group or participants, and unpaired is when those data points are unconnected, i.e. a between subjects design. So we're going to use that to explain the amount of variance that is attributed to chance and the amount of variance between our groups that we can have some confidence is as a result of variations of our independent variable. So to do this, we first need to determine a null hypothesis. This null hypothesis is the central part of our test. And the null hypothesis is always that there is no difference in a dependent variable between an independent variable and the other independent variable. So in this case, you've got two levels of independent variable. So if we express that in terms of our kind of text entry stuff, we might say the null hypothesis is there is no difference in words per minute between finger input and nose input. So we're then going to use that null hypothesis to perform the test. And what we'll either do is one of two things. We'll accept the null hypothesis, conclude that yes, there is no difference between finger input and nose input, and we'll reject our alternative hypothesis. And our alternative hypothesis is that there is some kind of difference. There's various versions of that. Or we could say, nope, that null hypothesis is not true. We're going to reject that and we're going to accept the alternative, that there is a difference. So that null hypothesis and the fact that there is no difference, this is what we're testing. We're testing to see if there is no difference, which is kind of backwards from what you would expect. So we're going to explain the difference between our two means by testing to see if there is no difference. Kind of like double negative or whatever. So we can have different versions of a paired test. So we've decided we're going to have a paired t-test because we're comparing things contributed by the same participants. But we can either do a one-tailed t-test, which tests kind of one direction. It determines that X is better than Y. Or we can have a two-tailed test which tests both ways. So all that does is determine there is a difference. That difference might be X is better than Y, or it might be Y is better than X. And there's kind of benefits and costs associated with picking one of these two options. And it kind of depends on the context of what it is you're doing and whether you have already some evidence maybe to suggest that one is greater than the other. So in this case, we have an example of finger input has a smaller words per minute than nose input. So it's less good, less effective. In order for me to get that, so that blue area there, this is an example of a bell curve where that minus 1.645, that is my two standard deviations away from the mean. So that blue area is greater than two standard deviations away from the mean. That shaded area under the curve is 5% of the total area. So I'm only testing in that direction, in this case, smaller. But I need less data to do it because that entire 5% of difference is focused on one side of the curve. So this is fine if I have a sense of what direction it's going to be. But there are some situations where I don't want to do that, because all that I'm going to do with this alternative hypothesis is I'm going to assess whether or not they are the same or whether one is better. So finger input has smaller words per minute, right? But I'm not going to test it the other way around. I'm not going to test whether nose input has a smaller words per minute. So imagine I have a drug trial and I have an existing drug and a new drug, and I want to test that one is better than the other, whether that's side effects, efficacy, metabolism speed, whatever. I don't want to commit myself to suggesting that one might be better than the other. I want to test all three ways. I want to know that there's no difference. I want to check if the existing one is better, and I want to check if a new one is better. And to do that, I can do a two-tailed hypothesis. Now, see that blue area under the curve? What's happened is my 5% that I had, so my 5% kind of, I want to be 95% sure. So I've got 5% variable to play with. That's now split in two. So I need to get more data in order to reach significance, or for my data to be significant. Jeez. I need more data in order to show significance, but I can have that broader hypothesis. And my broader hypothesis here is that there is a difference. I'm not specifying any direction, I'm just saying that there is a difference. So this is what I have gone with based on the fact that I have a within subjects design. I've selected a paired t-test. I have a non-directional alternative hypothesis, and my alternative hypothesis is that there is a difference in words per minute between finger and nose input, and so I want a two-tailed test. So I'm going to want a two-tailed paired t-test. Now, I can do this on lots of different things. I can use an online calculator, I can use R, SPSS, MATLAB, Excel, any other variation of stats software out there. We're going to do an Excel test. So if you run it on Excel, you'll get something that looks a bit like this. Now, we're going to go and have a look at that in more detail when we actually meet next time. But I just want you to see what that will look like, so that by the time it comes, you kind of have a sense of what those values are and what you're looking out for. So, things we need for the test. We need three things for a t-test to make sense, to be actionable. We need to know the degrees of freedom, the alpha, and the critical value. So if we take each of them in turn, the degrees of freedom this is the number of values that can vary within your sample and still give you the same mean value. So that is n-1, effectively. So if you imagine that I have an average, I've got three numbers that give me an average of 10. And that average is calculated from those three numbers. Now, once I select my first two, the third one is fixed, so I have no freedom in that third number. If I swapped that out for another number, it would need to be the same, else my average changes. So every number, apart from that last one, can change and still result on the same mean value. And so that's why my degrees of freedom for this example is n-1. So I have, in this case, three numbers, so my degrees of freedom is 2. If I have 20 numbers, my degrees of freedom will be 19. So that's important because that is going to help us calculate the critical value, which we're going to come on to. The second thing is the alpha, or the confidence interval that we have. So this is expressed in statistics, that's alpha, and we will need to combine that with the degrees of freedom to get our critical value. Now, if you want some more detail on the critical value, because it is the critical part and all that, there is a YouTube video there that you can go and have a look, and that will give you a bit more in depth on how that's calculated for one-tailed versus two-tailed, at both ends of the tail for one tail as well. I'm just going to tell you about a two-tailed one because that's the kind of test that we've done. So what I need to do, so I said I had degrees of freedom and a confidence interval or an alpha. So if I just escape this for a second, I'm going to take you to a t-table. So you can find these t-tables online everywhere. Nowadays, modern stats packages tend not to require you to go and look these up because it can be done computationally. This harks back to the days when t-tests were done by hand, which you can still do if you're interested. You can set up an Excel spreadsheet that will do all the calculations in each column and then give you kind of the values you need at the end. It's an excessive process when you can just type t-test. But what that critical value is, now there are two versions of these. There is a one-tailed distribution table and a two-tailed distribution table. I've obviously got the two-tailed one, and I'm interested in my degrees of freedom right the way down here is 14, let's say. So if my degrees of freedom is 14, I'm then looking along these columns in order to find the appropriate one that has the correct alpha value or the correct confidence. So I know that I'm looking for 0.05 because I want to be 95% sure. If I'm doing a clinical drug trial, I'm probably looking at this 0.001 category. Very rarely will you use statistical significance at 90%. Generally, if you've got no good reason for using any other one, you use 95. So that's an alpha of 0.05. If I combine those two rows and columns together, my critical value is 2.145. So in this case, I've added that in here, my critical value of 2.145. Now, because I have two-tailed, I have the positive value at one side and the negative value at the other side. Because remember, my mean is in the middle, and that's 0. So if my t-value, the t-value that I will get from my t-test, so the result of my calculation, is greater than the critical value, it would fall into this area here that has the shading on the right-hand side. If my t-value is negative, it might fall into the one on the other side. And you can see that my alpha value is split between those two because it's two-tailed. So let's say my t statistic, my t-value that I get back from the result is 2.5. That is greater than my critical value and therefore in the shaded area, and that shaded area is the rejection zone. So if it's in that shaded area, we're going to reject the null hypothesis. And in this case, we are, by default, going to accept the alternative hypothesis. The alternative hypothesis is that there is a difference. So we can't make any assumption on what direction that is from the test that we've done, but we know that there is a difference. Now, it's fairly common for people to make a hypothesis on, because we need more data, right? Make a hypothesis of one kind of t-test, and then when it's not significant, they make a different hypothesis that will be significant. This is called p-hacking. So it's not a good thing to do. It's basically cheating the statistics. So what you need to do is make sure that, in this case, we've picked there is a difference. Are you sure that's the alternative hypothesis you want? You want to make sure that before you start doing your test. So Right, we're at that we have a critical value, we have our t value or t statistic from my calculation. That falls inside the rejection zone when I compare it against the critical value, and therefore I'm rejecting my null hypothesis. So when I want to express that as kind of a written thing, if I want to express that in a research paper, for example, I need to report those three things. I need to report the t value. So that will be the t value that I get from my test. In this case, it's 2.145. So it's the same. I think I've made a mistake, but I need a t value, t statistic. I need my degrees of freedom, and I need my level of significance. My level of significance is this p value here. So this is a super, 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 super significant result. So I will say a paired samples t-test was conducted to compare finger input and nose input conditions. So it's important for me to say that I did this kind of t-test and it compares these two things. Because when I say that I did paired samples, you know what kind of experimental method I was using, and you can match it up and make sure that it's appropriate. We can then continue. There was a significant difference in the scores for finger input, provide the mean and standard deviation, and nose input, mean and standard deviation conditions. Then I have the t statistic for those degrees of freedom is 2.145, and my significance value is. That is all you need to do when you're reporting statistics. It's up to then the reader to interpret that and figure out what that means. So it seems like an awful lot of work has just come down to these two sentences. But they're two meaningful sentences, so it's worth it. So that concludes our mini-series on statistics, hypothesis testing, t-testing, whatever it is we're calling it. I think I've called it everything. What we will do when I next see you is that we will go through the analysis of some results from the text entry study. We will we'll do a t-test, maybe do a few t-tests just to see if we can find any differences between them. We will also have a little look at the NASA TLX and see if there's any kind of interesting stories to tell from that. Until then, have a good time. See you then.